This video is on calculating standard enthalpy changes of reaction given an enthalpy of formation. So enthalpy of formation is the amount of heat it takes for 1 mole of a compound from its elements. So think of formation as like what individual elements make up a compound. So the magnitude or size depends on things like temperature, pressure, and state, so solid, liquid, gas. We compare to standard state conditions, so like a specific temperature, pressure, things like that, like what state would they be in. And we can find these formation values in table 12 of our data booklet. So if you have not been given this yet, there is a PDF of it in your school resources folder in Schoology. So you might want to open that up if you don't have the actual data booklet yet, but I'll be accessing it in the video too here to show you what that is. So talking about formation, like what would the reaction look like if we were forming C2H5OH, so ethanol. So if I write a reaction like this, C2H5OH, and we can talk about ethanol, its standard state would be a liquid, like if we had it in the room at this temperature, at this pressure and such. So what elements make this up? Well, you, I think, can figure this out. Carbon would be one, obviously. And carbon is in things like the graphite in your pencil, it's in diamonds, it's in coal, it's in every living being, and its standard state would be a solid, and more specifically, it would be graphite. That would be its simplest, most basic form. All right, so then we also have hydrogen, and you know that hydrogen's diatomic, so it would be H2, and I hope you know or remember that hydrogen standard state would be a gas. And the last piece would be oxygen, also diatomic, and also a gas. Now for this formation, this would have to be balanced. So if I look at my carbons, there's 2 in ethanol, so I need a 2 here. For hydrogen, there are 6, 5 plus the 1, so I need a 3 here. Now the problem with this next part is that oxygen has 2 on the reactant side, but only 1 on the product side. And we can't just write O, because we know that oxygen's diatomic won't stand alone by itself, but we do need to keep this coefficient right here. We need to keep it at a 1. Oops. And I'll show you why more in a second, but in order for that to be 1, we have to put a fraction here. So this is one of the times it's allowable to have a fraction as a coefficient. So now, when we talk about this delta H of reaction for ethanol in its standard state, we can look this up in the table. So this is what the table looks like, table 12 in your data booklet. And if I find ethanol in here, I'm gonna, let's see, where do we go? Right here. So ethanol, C2H5OH, liquid, and here's our delta H of formation, negative 278. And if I look up at the units right here, these are in kilojoules per mole, which is why, oops, I went the wrong way, sorry. Which is why, what did I say this was? Negative 278. Which is why this had to be 1, because this is the amount of heat per 1 mole. If that was a 2, if we had to balance it that way without fractions, then that value would change. So with this, how did we get from that formation on the table? Like that's a formation, delta H of formation. How did I decide that this was the reactant or the reaction delta of H? Well, it has to do with the fact that our delta H of reaction we can find from all of the formations. So our equation for this is delta H of reaction is going to be the sum, and I think you've probably seen this symbol in math, the sum of all the delta H of formations for the products minus the sum of all our delta H of formations for all the reactants. And okay, so I'll come back to that. Sorry, I'm trying to figure out the order I want to go in. So enthalpy is an extensive property. And if you remember from talking about physical properties, they can be intensive or extensive. Intensive doesn't depend on the amount, extensive does, which means like intensive is like density. No matter how much water you have, its density is 1 gram per milliliter. Enthalpy is extensive. The amount changes your value. So if you increase the amount of reactants, like if you have I don't know, 3 quarts of water that you're trying to boil on the stove versus 1, your amount of heat will increase. You'll need more, you'll have to add more heat to raise the temperature to the same value. Enthalpy change for any reaction is equal to, but the opposite sign for the reverse reaction, which we've talked about. And the enthalpy change for a reaction depends on the state of the reactants and products. So make sure you're looking up very carefully your delta H of formations with the correct state. All right, so one other thing to note is that elements in their standard states have a delta H of formation of 0. That's why when I go back to this, our delta H of formation is just the, our delta H of our reaction right here is the delta H of formation of our ethanol minus, that's our product, minus all the reactants, which all of them would all have a delta H of formation of 0 because they're all in their standard states. All right, so now let's find something like this in this example problem where it says find the heat of the reaction. So we're looking for the whole thing, not just a formation of one piece. But we're going to find the heat of the reaction based on the delta H of formations. And the math is not as complicated as it may appear from that equation up above. Okay, so this, let me fix that. That should be a yield sign. I don't know what happened there. All right, so our delta H of reaction is what we're solving for. And we're going to look up all the formations. So let's look up the first one, CH4 as a gas, methane. It's the very first one on here. As a gas is this, -74. So I'm going to write right underneath it, -74.0 kilojoules per mole. All right, O2, if I look at this table, the O2 is not on here. And that's because it is an element in its standard state, which would be a gas, just like we talked about in the previous part. So that's 0. All right, if I look up CO2 as a gas, way down here on the bottom, CO2 gas is -393.5. So -393.5 kilojoules per mole. And then water, if I go, oh, wrong way, sorry. Also way down on the bottom. Water is H2O. We got to be careful. This one was a gas. Or so, no, sorry, this one was a liquid. -285.5. Okay, so we've got all our individual delta H of formations. Now we can use this equation, sum up the products, sum up the reactants, and then subtract them. You could do this as 2 problems, like you could do like this step first, and then you could do this step second, and then you could subtract them to find your delta H of reaction, or you can plug them all in one time. I'm going to write them all in one time. Let's see how this goes. You got to be a good bookkeeper here, though. You need to pay attention to what you're doing, and I highly recommend you put in units and you put in zeros as appropriate, like I'm going to do in this example. So my delta H of my reaction. Okay, so I'm going to do all of the products in brackets here. So I'm going to do CO2. So I've got -393.5 kilojoules per mole. So I need to look at this and say, well, how many moles of CO2 are there? And there's only 1. So I'm going to write times 1 mole. And I know you're thinking, oh, times 1 doesn't change anything. Correct. But what I can see here is that my moles will divide out. So that's my first product. My other product, right? I have to sum up all of my products. My other product is -285.5 kilojoules per mole. And this one has 2 moles. So I'm going to have to multiply this by 2 to get that value. Okay, and then I'm going to do end bracket here. So these right here are all of my products. Okay, so now we're going to subtract from them all of my reactants. So I've got -74.0 kilojoules per mole. And there's only 1 mole of that. But I'm still writing that so that I am aware and not forgetting to do that piece. And then I'm going to add to that the 0, and I'm going to write 0. So I know that I've got all of my pieces there, and these are all of the sum for all of my reactants. All right, so now it's a matter of typing this in your calculator. I would pause here, make sure you can type it in correctly, because the answer when I type it in is negative 891.1 kilojoules. Okay, so if you don't get that, try it again, and if you still don't, come talk to me in class. So that's part A. Part B now says how much heat is released in the above equation if 4.5 grams of methane is burned under constant pressure. So now what we can do here is when we're finding how much heat is released, right, it's exothermic, that's the negative up here. We're trying to find how much heat per mole. So we need to convert this mass to moles, put that here, there's our heat, and we can divide. So 4.50 grams of methane, and if I find the molar mass is 16.05 grams per mole. So if I take 4.50 divided by 16.05, I get 0.280 moles. And my delta H then is going to be my negative 891.1 kilojoules over 0.280 moles. And so I get a value of negative 3,560 kilojoules per mole. So for each mole of methane, it's going to combust with 3,560 kilojoules, and it will be exothermic, hence the negative sign there. So that's using delta H of formation to find a standard enthalpy change for a reaction.